So welcome to lecture 38 of MCS 471, an introductory course on numerical analysis. And for today, we start a new chapter on partial differential equations. In particular, we look at the heat equation, which is quite proper for the season, as we all need heat. So everybody's warm. So we will see three methods to solve the heat equation. The first method applies forward differences and leads to a simple explicit method. It's a time-stepping method. Unfortunately, the method is not stable for any step sizes. So stability analysis will show we often need to take very small time steps or otherwise the solution will blow up on us. So the second method applies backward differences, and that is a method that is unconditionally stable, although still not that accurate. So we still may need to take step sizes that are too small. So we will end with the method of Crank-Nicholson, which is unconditionally stable, and for which the accuracy is already quadratic in the step size. So the expected error will be of order h squared. H is the step size. All right, then let's get into partial differential equations. So a partial differential equation is an equation that involves many partial derivatives. So unlike with differential equations, we no longer use the prime notation because we have two independent variables. Here, in general, the independent variables are x and y. So the dependent variable is a function of x and y. So we have the partial derivatives that are written here in full. There is a right-hand side function, or similar to a right-hand side function, the capital F, which is a function in the independent variables, x and y. The variable, the function that depends on x and y, the u, and then the partial derivatives, so the two partial derivatives with respect to x and y. So for the heat equation, we will consider time as another independent variable, and we can then still use the letter y for our approximations. That will be convenient. So we will see only a little bit. We will only do a very small introduction to partial differential equations. Today we focus on the heat equation, and this equation is an example of a parabolic partial differential equation. So with the three coefficients a, b, c, we form a discriminant. If the discriminant b squared minus 4 times ac is 0, then our partial differential equation is of the parabolic type. And the main example that we will consider today is the heat equation. In the next lecture, we will consider the wave equation. And the wave equation is when the discriminant is positive. So these are parabolic partial differential equations. When the discriminant is negative, that will be the subject of the third and last lecture on partial differential equations. When that discriminant is negative, then our type is elliptic. And these type of equations describe steady state. All right, what is now the heat equation? So here is the general form of the heat equation. So what do we have? So we have two variables, x and t, so space and time. So in an interval, we measure the temperature, so a finite interval from A to B. This is where the x lives. And then we have the time interval starting at 0. So the time interval will lead to our stepping. So, and what is important is, if you look at the heat equation, is to recognize that the differential equation here looks very much like an initial value problem. So if you focus only on the first two equations, then we have the derivative with respect to time, which is proportional to the second derivative with respect to x. So the derivative with respect to time is proportional to the second derivative in space. And at time equals 0, we have an initial temperature distribution, here represented by the little f. So little f is a function of x. We know initially in our interval what is the initial temperature. But by the way, I'm not explaining why this is the case. So this is outside the scope for this course. Why this makes a valid model comes from material science. So in this course, we are mainly interested in solving this equation. So the first two equations might look this to an initial value problem. But then you see that with the last two equations, we have a boundary value problem. So we have an initial value problem for time, but we have a boundary value problem for space. So at the endpoints in the interval, we know the temperature distribution for times. So this problem is defined by a constant d in coefficients, which is positive. The right-hand side function f space, and then two functions L and R, which are depending on time. So these two functions define the temperature at the end points of the interval. So that is the setup of the general heat equation. Finally, you will get one of the three types of equations, and I will not tell which equation it is, so you will have to be able to recognize the shape of the problem, if it is a heat equation, a wave equation, or a steady state. That will be the first critical part in dealing with the problem. So I will spend quite some time in characterizing the format of each PDE that we consider. So remember, initial value problem in time, boundary value problem in space. So this is a two-dimensional problem. Here's our running example. Recognize here the space. So we have the plane, we have x from 0 to 1, and then we have time coming from 0 to 1 as well. So we have an initial temperature distribution. So the initial temperature is described by a positive sine function. So the temperature is positive, the fusion constant is 1, and at the boundary, assuming that our interval is insulated, the temperature there is 0. And you see, what we expect is that since there is no heating provided at the endpoints, we expect that the one-dimensional interval cools off. So at the end of time, it's already for t equals 1, the temperature is very close to 0. So we have also here an exponential decay. So we have a decaying solution. That's important in what will follow. So we will consider 3 methods. So the first method applies forward differences. Differences now applied to 2 dimensions. So we are discretizing in space. So here we divide our interval AB in 4 equal parts. We have 3 interior points, and we also work with a time interval. So time can go on, and we have a capital T that is on time. So our grid, the discretization of space and time, produces a grid, a spacing in time and a spacing in space. So the red dots here, reading this 2-dimensional grid from left to right, you see that each time, in each time step, we compute the values for over the space, the 3 internal values, and we go filling up the distribution. So this is a time stepping method. So we go forward in time. So what are the parameters here? So it will become a linear algebra problem. So the leading dimension, the main dimensions, are the number of points that we have in our grid. So on the example here, we have a grid where we are doing 4 time steps. So let me draw what are the grids. So we have the red dots, and the red are the unknowns. So it's important to remember that we have an initial temperature distribution. So at time equals 0, we have the function f that will define what is the temperature, and then we have a left bound and we have a right bound. So we have the 3 functions. So r is a function of time, L is also a function of time. So the black dots are the points where we know what the temperature will be. The red dots is what we will compute. On this example here, we have 3 internal points in space. So the M determines the dimension of the system. So the M will be 3. And then we have 4 time steps. So the big N will be 4. So this will lead to a system of 12 unknowns. I'm sorry. So each step we will have a system of 3 unknowns. But we have, all in all, we have 12 unknowns. So we will do 4 time steps, each time solving for the 3 unknowns. So what is the time stepping formula? Well, we will apply in time the forward difference formula. So the forward difference formula keeps the x constant. So if you want, you can actually imagine that the x is not there, it's just a letter. But we have the time step in k. So I forgot to mention, so we have the leading dimensions, the capital M, the big M, the big the little a, little k. So h is step size in space, k step size in time. All arrays there start at 1. So one has to be a bit cautious about this. Also, the time step, if we are saving everything, we will actually start at 1 if we each time, if you return higher matrix of all the points. So I was ending with, so the last line on the slide gives the time step, the application of the difference formula. So this is a Taylor expansion. What is important here to note that the accuracy, so the term that we're going to forget about, depends on the second derivative. So there is some constant, C2 here, it's a constant on time only, and the order of this formula is linear in K. So that is important here. So our time stepping method will be, so the error that we may expect from that will be of order K. So if you have a step size of 1/10, then do not expect more than 1 decimal place accuracy. If you want 2 decimal places accuracy, your time step has to be at least 1/100. So that's important to realize. All right, so we have our forward time method. Then we have the second part derivative from the right-hand side of the differential equation. And there we apply the central difference formula. The same central difference formula that we applied when we consider the 2-point boundary value problems. And that formula has a much higher accuracy, so the accuracy there is of order h square. So that is important here too. So the formula comes from our the error formula comes from our Taylor series expansion. It also depends on the shape of the function. So you have the higher order partial derivatives that are sitting in there. You recognize the coefficients 1, -2, and 1. The coefficient matrices will be tri-diagonal. Okay, we have the formulas. Let's now start deriving the system, or actually the algorithm. We have the equation. Now it's a little bit awkward that the order is flipped. So we have the d times the second order derivative, although I realize why it is flipped. We ended second order differential. And here we have the to right, we have the time step. So combining the truncation errors, we have a linear approximation essentially. Given that h and k are of the same order, or as we will see, the time step, the k actually needs to be of much less. If we want accurate results, will need to be much less than the h. We are computing so approximations. So what is important here, and it's important that I mention this because the slides are actually kind of lacking in that regard. So we have a grid of two variables, and the y, so we haven't actually used the y in the heat equation. So our two independent variables are x and t. We have the u, which is our function, and the I, the first x, concerns the space. The second index, the j, refers to time. So that is important connection that is missing, which I just wrote down. So our time stepping formulas will give approximations for the values of the unknown function u. These are two-dimensional formulas, but so here it's implicitly there. So we have the two independent variables, the x and the t, that we can choose. And then we have the dependent variable, which is u, and that gets approximated by the y. The formulas are explicit. Assuming that we know the past, we can predict the future. So you observe that the formulas at the right-hand side are all, so this right-hand side here, they all involve j. So j is the index of time. This is an explicit formula. An important, a very important constant that comes out here is the sigma. So the sigma is here introduced to simplify the notation, but the sigma will also be important later on. So it involves all the important letters, the diffusion constant, the time step k, and the space step h. So we can visualize the method by what is called a stencil. So we do the time stepping in the vertical direction here. So we go from time 0 to the capital time, the end of our time interval. Each time we use to get the point here, so this is our unknown point that we compute, the yij plus 1, we use the information from at the previous location and the two neighbors. So this stencil shows also, it visualizes that we are dealing with an explicit method. So there is no system of linear equations that need to be solved. However, it's still important if you want to organize your computations that things are written in matrix vector form. So we have a vector of points, an array of values that gets updated each time with a matrix vector multiplication. And we take into account also the values at the boundary. So here we see the dimension of the problem. If we are working with the m minus 1 is here the dimension of the linear problem, so the total number of variables that we keep in each step, so the minimal number of variables that we keep in each step. So it's a tri-diagonal computation, so computing this matrix vector product proceeds in linear time. And here is the Julia function. The Julia function as defined in our, the Julia function that defines the time stepping formula on our running example, although the function is quite general. So we have the parameters in the heat equation, the diffusion constant, the initial temperature, so F naught is a function in x. The LB and the RB are functions of time. Then we have the bounds for the interval A and B, and then the time, capital T, the limit of time interval. M and N are the dimensions. So what we will have on return is an M by N matrix. M stands for space and N is for time. The function, here it is important that we figure out what is H and what is K. So we return an M by N matrix. So the spacing, so it's important that the H and the K are well defined respective the dimensions. You recognize the sigma, so the parameter is defined here, and the construction to make a tri-diagonal matrix. We initialize the result with the application of the boundary condition. So the initialization, as it will go here, the initialization will apply, will initialize our result. So here it's again a bit unfortunate that everything has to start at 1, but the result is an M by N matrix. So when, and this also then explains why we have here the N minus 1. So the K at time, we will do N times steps, actually N minus 1 time steps. So end of time, when this actually N minus 1, we will end up at time T. Matrix A multiplies the result. So you may ask why we need this entire matrix. Well, this script, this function was used to produce the plot that was shown at the very beginning. All right, let's apply this. We do this with 6 values. So the first column, so this is a column, this first column here is the initial temperature. The last column, and I will immediately already indicate what is most important here, is that the last column gives the values of the temperature at the end of time. You see, we started with a temperature range between 0 and 1, so the square of the sine function, but we end up with huge temperatures. So we were expecting that our interval would cool off. There was no heating applied, and when time goes on, but instead the temperature blows up on us. So This was kind of deliberate. So do have this m value. So the m is related to h, and the n is related to k. So if one wants to use this method to make the plot, then the k needs to be a lot less the h, or equivalent to the capital N. You need to do a lot more time steps with a finer step size than the spacing. And the question is, why is that? Why do we have this? All right, well, what are we doing in this method? It's a very simple method. We are multiplying a matrix with a vector. So where did we do this before? Well, remember power method. And the power method produces the vector that is corresponding to the largest eigenvalue. So we make these products, and the vector will actually grow unboundedly if the norm of the matrix is larger than 1. So the problem is that the largest eigenvalue of our matrix A should not be larger than 1. So that gives actually the stability analysis. We can verify this because we have the matrix and we can compute eigenvalues. So for the example with 6 both m and n, we see that the spectral radius of the matrix is larger than 1. It's 18, which is a lot larger than 1. The critical parameter here is the sigma. So by choosing n equals to 250, we get a lot smaller value for the spectral radius. You can see that 20 and 1000 is very close to 1. So the value that I picked here in making the plot is actually quite on the edge. So we have value 0.99 for the spectral radius for the true norm. All right, so there is a theory behind this. We will not go into the proof, but the condition is on the sigma. So the sigma should be less than 1/2 for the forward difference method to be stable. So we can verify on the numerical example using the diffusion constant equals to 1. The divergence happened when the convergence, the critical threshold parameter was sigma was 0.4. So we conclude that the forward difference method is a simple method, explicit method, but its stability is conditional. It means that the step size in time needs to be at least 1 order less than the time step, than the step in space. So that makes that applying this forward difference method does not always lead accurate results or efficiently, quickly. Our first exercise is applying this theorem. So if we are thinking about the final exam, then this could be an exercise, except that the first line will be wiped out. So the heat equation, you will to recognize that this is an equation. So, and all parameters are there. So the diffusion constant is 1. So the diffusion constant is not explicitly mentioned, but this is also something that one needs to recognize. We have given the M, and then the question is, you can formulate, based on M, you can formulate what is the H for the interval 0. And what is the D, the K is 1 over. So what is the threshold on K or on N so that the sigma that you can make is less than 1/2? So it is the evaluation of the formula from the theorem. So a very straightforward application. The bound can also be verified experimentally. All right, so let's now look into other methods, two other methods. This may seem familiar to Euler and the backward Euler. Let's apply the idea of backward Euler. We will use the backward difference formula to approximate the time stepping formula. So we have the same accuracy. So we will still have that this formula here will be having an error that is linear in K. So this is what this term essentially means. The second partial derivative with respect to time is a constant, depends on the constant C naught and also the fixed value for Y. So then we obtain, so for central difference for the space discretization, nothing changes. So we have the same formula, but except now that if you look at the formula and we rearrange, so we have terms in J and terms in J minus 1. J minus 1 is in the past. The term comes all by in the right-hand side. We also have the sigma that shows up again. So let me point that out. This constant here occurs multiple times, so it occurs 3 times, is the sigma that we had before. But now you see that what we have at the left are 3 values at the current time step. So this method that then will not be explicit. It will be an implicit method, just like the backward Euler method that we used for solving initial value problems. We can visualize this. So we have the general equation in the sigma, which is a tridiagonal equation. And the picture, the stencil of the method, shows that if we are going forward in time, again, we should read this upside down, go from the bottom to top. If we march forward in time, we are computing the next 3 values based on the single previous value. So this seems like a very awkward thing to do, but we can solve systems of linear equations. So we still remember this from a very long time ago, from the beginning from the course. So if we can solve linear systems, then actually we can do this time stepping. It's that in every step we will need to solve a linear system. So the general formula for method is expressed by a tridiagonal linear system. And here this is denoted in short with the inverse, but typically we will not do this. You can also see why iterative methods might be applied here very naturally. So this is done for very large problems. And we have already, from the previous time step, already some good idea on how to update the matrix. The matrix, by the way, is also diagonally dominant. That is another issue. But we will, in our simulations, we will just apply the backslash operator. All right, so let's do this. So we have a Julia function that looks very much the same as the function that was shown in full previously. Here I will just denote the main differences. So now we have a matrix, a tridiagonal matrix again, that involves the sigma constant. And the main difference here is that in every time step, we solve a linear system with the slash operator. All right, when we are running now our method on the same very, very large values, we see that we are no longer diverging. So this is very good. Perhaps I should emphasize this. So the end values are all bounded. So our temperature is indeed this is not accurate. It's no longer. That's the conclusion of this experiment here. So the picture was made with the forward difference method. Let's try to make the same picture, but now actually you may be able to relax the bound, or perhaps not. So the methods still have the same accuracy. So the question in this, so in this method here is that can you produce more accurate approximations? So compare the end value. So if you run the simulations, you have one last column, compare the last column. See, so you same value for m, but can you do fewer time steps with this backward difference method? All right, so I'll consider the last method. So I have about 5 minutes left, and that is sufficient. So the problem with the backward difference formula is that it is not very accurate in time still. So the error, although it's not blow up on us, it's stable. The what we actually want is also an error that is quadratic. So we will apply a weighted combination of the differences. So we have another discretization for space, and for time we will also use the forward differences, yes, we will use the differences that are shown here. So notice that we are having a weighting. So here we have the J. In the second term, we have the J minus 1. So we are mixing the differences. We then obtain a more complicated relation. So it's also an implicit relation. So we have at the left all the J's in the last equation, and at the right for J minus 1. Fortunately, the equations are still tridiagonal. We can visualize the formula, and there are two main properties of the formula. The local error is quadratic, both in time and both in space. And the method is unconditionally stable. So there are no restraints on the relationships between H and K. And this is the method of Crank-Nicholson, where we have two triagonal matrices. So in every step, we will do a matrix vector product. We did with the forward. We will, in every step, also need to solve a linear system, like we did with the backward differences. So the method of Nicholson can be seen as a combination of forward and backward differences. But the method is still it's still short enough to describe. So now I have a B appears in multiplication, and here we have the solving of the linear system using the coefficient matrix A. So the method is defined, so it's defined in Julia function. When we run the Julia function, we get more accurate results. So the temperatures are positive, but you see the temperature fluctuation. So we actually end up with also negative values, which in the oscillation of the sine function might be more plausible. So that's essentially it. I will end. So the main difference is, let me emphasize this. So the main difference between the backward difference and the Crank-Nicholson method is the time stepping. So one last example. It's quite, if you solved exercise 2, then with exercise 2 you couldn't really gain too much more accuracy. But here you may expect that by applying the method of Crank-Nicholson, you can actually reduce the capital N, doing it much closer to the capital M. So we have a more accurate method and consequently a more efficient method to solve the heat equation. Next time, the wave equation.